My name is Jim Pettigrew, and I'm the Director of the Gulf Research Program's Offshore Energy Safety Board. I'd like to welcome you to the National Academy of Engineering and Gulf Research Program's Offshore Energy Colloquium series this morning. Today's colloquium is part of a series organized by the National Academy of Sciences Gulf Research Program and the National Academy of Engineering. This colloquium series is planned to occur 3 times a year with the purpose of addressing topics around the production and transportation of offshore energy and their contribution to a net zero offshore energy environment. To learn more about the Gulf Research Program or to watch recordings of our past webinars, please visit the Gulf Research Program's website at nationalacademies.org/Gulf. And similarly, for more information about the National Academy of Engineering, you can find that at the NAE website at www.nae.edu. Please note that this webinar is being recorded. This includes audio, video, chat sent during the meeting, and by joining this webinar session, you consent to such recordings. I'd like to welcome all of you and thank you for joining us today. We'll start the webinar with a presentation from each of our 4 panelists, and that will be followed by a moderated question and answer session. We'll have the recording of this webinar available on our websites within about the next week or so. If you're listening live, you can ask questions by submitting them through the Q&A box, the balloon box there on the bottom that says question and answer. And we will take those questions and ask those at the end during our moderated question and answer session with our panelists. So questions will be answered by all our speakers' remarks after our speakers' remarks, but they can be submitted at any time during the presentations. Please note that we do have more than 500 people registered today for this session, so we may not be able to get to everybody's question. Thank you again for joining us today. I'd personally like to thank Ms. Courtney Hill for all of her hard work behind the scenes in making sure everything was set up properly and on time for our presentations today. But most of all, I'd really like to thank our esteemed panelists and our moderator for participating and sharing their expertise, perspective, and insights. Now it's my distinct pleasure to introduce our panelists for today's colloquium. Today, you'll first hear from Ms. Sharon Matthews. Sharon manages all resource management functions for offshore renewable energy, alternate use, and marine minerals development on the U.S. Gulf of Mexico's OCS. She has worked for the Department of Interior for more than 12 years, and during her tenure, she's played key leadership roles in advancing the National Sand Inventory Initiative for the Marine Minerals Program in the Gulf of Mexico, developing the Renewable program in the Gulf of Mexico, and implementing a more interactive format for outreach initiatives. She holds a bachelor's in biology from Xavier and a master's in public health from the University of Southern Mississippi. Next, you will hear from Dr. Barbara Cates Garnick. Dr. Garnick is a professor of practice and senior research fellow at the Fletcher School at Tufts University. And most recently, she served as the Undersecretary of Energy for the Commonwealth of Massachusetts, where she was responsible for guiding energy policy. She also served as the co-chair of Massachusetts Global Warming Solutions Act Implementation Advisory Committee that oversees the implementation of the Commonwealth's Global Warming Solutions Act. She has had an extensive career in energy, environment, and clean technology that has spanned the private and public sectors and included the creation of a clean technology incubator at New York University Polytech, where she also taught courses on energy policy. She served as corporate officer at a major U.S. utility, a consultant on strategic energy initiatives, and as a public utility regulator. Now, after Dr. Garnick, you'll hear from Dr. Danielle Merfeld. Dr. Merfeld is the Chief Technology Officer of GE Renewable Energy, reporting directly to the CEO of that company. In this role, she leads technical efforts to develop differentiated products and services across the broadest renewable energy portfolio in the industry, including onshore wind, offshore wind, grid solutions, solar photovoltaic, batteries, and hydro. She also champions sustainability efforts across the business, leading a team focused on achieving carbon neutrality. Got out of order, and leads the GE Renewable Energy Edison Engineering Program. Prior to her role at GE Renewable Energy, Danielle was the Vice President and General Manager at GE Global Research, where she advanced disruptive technology platforms across the industrial sector. As a thought leader in the industry, Danielle has delivered remarks and participated on panels at conferences and symposiums on topics like digital platforms, advanced controls, and energy transformation, the future of renewable energy, grid challenges, and solutions and microsystems. And finally, Dr. Kaushik Rajashekara will close with his perspectives. Dr. Raja received his PhD degree in electrical engineering from the Indian Institute of Science in Bangalore, India in 1984. Later, he joined the Delphi division of General Motors Corporation in Indianapolis, Indiana, as a staff project engineer. In Delphi and General Motors, he held various lead technical and managerial positions and was a technical fellow and the chief scientist for developing electric machines, controllers, and power electronic systems for electric hybrid and fuel cell vehicle systems. In 2006, he joined Rolls-Royce Corporation as a chief technologist for power conversion control technologies for more electric and hybrid aircraft systems. In August 2012, he joined as a distinguished professor of engineering with the University of Texas at Dallas. And since September 2016, he's been a distinguished professor of engineering with the University of Houston. He has authored or co-authored more than 250 papers in international journals and conferences, and has 35 US and 15 foreign patents, and has authored a book. His research interests include power energy conversion, transportation, electrification, renewable energy, and microgrid systems. At the end of these presentations, we'll have a moderated question and answer period, and our moderator today, we will have with us Dr. Al Romig. Al is the Executive Officer of the National Academy of Engineering, reporting to the NAE's president. He was previously Vice President and General Manager of Lockheed Martin Aeronautics Company, Advanced Development Programs, better known as Skunk Works. He spent the majority of his career at Sandia National Laboratories, operated by the Lockheed Martin Corporation. He joined Sandia as a member of the technical staff in 1979 and moved through a succession of R&D management positions, leading to appointment as Executive Vice President in 2005. He served as Deputy Laboratories Director and Chief Operating Officer until 2010. Dr. Romig was elected to the National Academy of Engineering in 2003 and the Council of Foreign Relations in 2008. Dr. Romig holds all degrees in material science and engineering from Lehigh University. Dr. Romig and our esteemed panelists, thank you very much for joining us today. Tashera, let's get the show rolling.
Good morning. Thank you, Jim, for this great opportunity. As Jim mentioned, I am Sharon Matthews, Chief of Emerging Programs in the Gulf of Mexico office, which is located in New Orleans. Next slide, please. The BOEM has 3 mission responsibilities as given to us through the OCS Lands Act and the Energy Policy Act of 2005. Those 3 mission responsibilities include offshore oil and gas, our marine minerals program, and our renewable energy program. Next slide. In January, President Biden issued Executive Order 14008. It announced the first ever national offshore wind goal to deploy 30 gigawatts of offshore wind by 2030, which would create nearly 80,000 jobs. So what is our path forward to achieve this goal by 2030? Next slide. On October the 13th, Secretary Holland announced our path forward for 2021 to 2025. This is our national leasing schedule. If you notice where all of the dollar signs are on the graph, that's where we have potential lease sales happening throughout the nation. Next slide. Next slide, hit one more time. If you notice, the Gulf of Mexico is highlighted to have a sale for late 2022, early 2023. As I mentioned, I'm in the Gulf of Mexico region, so I wanted to definitely highlight that we'll have that sale in late 2022, early 2023. Next slide. So this is the renewable energy process. It looks at the 4 phases that we have throughout the process. So we have planning and analysis, leasing, site assessment, and construction and operation. As most of you are aware, on the Atlantic, most of our projects are at the construction and operation phase. We are receiving those COPs, as they're called, within the office. So this is the phase that the Atlantic office is in right now. Next slide. So I wanted to give an overview of the actual renewable energy program throughout the nation by numbers. So we have completed 8 competitive lease sales. We have 18 active leases issued. We also at that construction and operation phase, as I mentioned, in the Atlantic. We have approved 1 this year. We have 13 that are under review. We have 4 that are anticipated to come into the office within the next 12 months. And as I mentioned earlier, we have 7 areas that are under consideration for leasing. And we were extremely excited to have still in the federal waters in 2020. Next slide. So how are we going to get to that 30 by 30? We have the estimated capacity for those construction operation plans that have been filed to give us 19 gigawatts. For the remaining lease areas, we have 8 gigawatts. So we do need additional lease areas to achieve that 30 by 30 plan. Next. So now I'm going to go a little bit deeper into the Gulf of Mexico. I'm going to give you a little bit of background information of how the program has recently started, talk about the renewable leasing process, and also the next steps for the program. Next slide. So last year, we announced 2 studies that were conducted by the National Renewable Energy Lab, NREL. The first study looked at a survey and assessment of ocean renewable energy resources in all of the Gulf of Mexico. This included wave, wind, and also solar. We also conducted another study to look at the economic feasibility of wind in the Gulf of Mexico. Is it economically feasible to have wind in the Gulf of Mexico? And if so, where? So these 2 studies sparked an interest in the Gulf. Next slide. So in October of 2020, Louisiana Governor Edwards sent us a request to initiate the task force. This actually kicks off the renewable energy process. So BOEM responded that we would have a Gulf-wide task force approach that will include all of the Gulf states except for Florida. If you notice to the map on the right, the wind speeds are a lot higher off of the coast of Texas and Louisiana, and they start to slow down and get lower as you move towards the east, towards Florida. We actually had our first task force meeting that was held on June 15th, 2021. The purpose of this task force meetings is to conduct outreach, engagement, to collect data and information. The members of the task force are state, federal, and tribal nations. So what are some of the advantages in the Gulf of Mexico? One of the major advantages that was pointed out in the study is the proximity to oil and gas and the supply chain. We're going to be able to leverage that existing capabilities and also that existing workforce and facilities that we actually have in Louisiana and other parts of the Gulf. So that's one of the major advantages for offshore wind in the Gulf. Of course, as many of you know, there are definitely challenges with hurricanes in the Gulf. But after speaking to several industry representatives, they acknowledge that the hurricanes are a challenge. However, with technology, they feel that they'll be able to overcome those challenges with hurricanes. Next slide. As I mentioned, the 4 stages of the renewable energy process, you can go ahead, next slide. The Gulf of Mexico is actually at the very beginning. We have not leased anything. We're in the process of working on a lease. So we're at that planning and analysis phase. We have formed that task force. We have issued the request for interest. We also recently issued the call for information. I'll talk about that in a little bit more. The next step for that would be the area identification, where we have this lease sale, what areas, and then of course the environmental reviews. And as I mentioned in the earlier slide, we're slated to have a lease sale for December of 2022 or early 2023. Next slide. So if you go a little bit deeper, you can go ahead, next slide. It shows the request for interest. That was published on June the 11th of this year. That included a 45-day comment period, which ended on July 26, 2021. Next slide. Now we're at the call for information phase, which was just announced on Monday, November the 1st. That includes also a 45-day comment period, which will end on December the 16th of 2021. So following that call for information, we'll do more in-depth analysis to determine those wind energy areas. Next slide, please. So when you start out planning these wind energy areas, you start from a very large planning area. So for us, it was the Gulf of Mexico, and you do a high-level screening to best find out what are those suitable areas for offshore wind. The NREL study definitely helped us to try to narrow down where those areas are. Next slide. So that helps after looking at where we think the interest may be. We were able to come up with a request for interest area to collect that information to see where is industry interested in, and what are some environmental concerns that we need to think about as we move throughout this process. It's definitely a winnowing down process. So next slide. So now we have a call area, which is going to be a smaller area, and I'm going to show you maps to show you how we're going from this larger Gulf of Mexico down to this small call area. So these areas will definitely be considered for leasing. However, we will winnow this area down even more, looking at environmental, soil conditions, military concerns. Those are just some of the factors that we're analyzing as we determine these areas, and also existing oil and gas infrastructure that is also in the area. Next slide. So the wind energy areas, once we have determined that area, they can be further divided into smaller lease areas, because companies may not want to bid on the whole area, so we can further divide that down into smaller pieces. Next slide. So this was a request for interest area that we published in June. It goes to the Alabama-Florida line all the way to the Texas-Mexico border. The water depth goes out to 1,300 meters to see if anyone was interested in floating wind technology. So as you see, it's a very, very large area. So that starts with the first process. Where are you interested in possibly having offshore wind? Next slide. From the RFI, we actually received 39 comments. 10 of those comments were from industry that provided us a little bit more information of where they're interested in their wind farm areas. Next slide. So from that information, we were able to come up with the call for information. As you see, it has definitely gone smaller. We're just west of the Mississippi River. A lot of that's based on soil conditions. Also off of Mississippi and Alabama, there's this Rice's Well area. There's also national parks, national wildlife refuges that are in their areas, potential migratory pathways that are there as well. So as we continue to analyze the area, we made it smaller, and it actually goes out to 400 meters of water depth here. And this, as I mentioned, this was just announced on Monday, November 1st. Next slide. So this is a combination map showing you the winnowing down process, how we have gone from the RFI area, which went out to Alabama, Florida. Now we're just off the coast of Louisiana and Texas, showing portions of our central planning area and the western planning area. Next slide. So here are some of the next steps. As I mentioned, November the 1st was when the call went out. That closes on December the 16th. We will hold a second task force meeting in January. We'll start that environmental assessment on the call area and identify those wind areas. In the process, we'll also continue our stakeholder engagement. We have planned some fishery workshops that will also take place in January as well. So as we continue to move through this process, we're gathering that information and data from our federal and state partners, tribal nations, and also the public, to better understand what areas that need to be included in the wind energy areas as we continue to winnow down the areas in the Gulf of Mexico. Next slide. And this is a list of our team members. We have our regional director, Michael Salata. We have our renewable energy coordinator, Adrissa Bube, our fisheries team lead, Mariana Steen. We have a data management team as well, Dana, and then we have our communications team. Next slide. And this is my contact information. If you have any questions, you can contact me here. Thank you.
Thank you, Sharon, for that great presentation, very timely as well. Our next presentation will be from Dr. Barbara Cates Garnick from the Tufts School. Bobby, please.
Thank you. Hello and good morning. My presentation is a follow-on from what you heard from Tashara. I'm going to talk a little bit about the policy challenges and opportunities from offshore wind. And I'd also like to give a shout out in my graphics and my slides to NREL, who provided a lot of very good background information. Next slide, please. As Tashara was talking, she was talking about a COP, construction and operations. I'm talking about the Conference of the Parties now underway in Scotland. Offshore wind is critical to a successful energy transition, much of which is being discussed today at the COP. It will enable us to reach a secure net zero goal in order to keep the mid-century limit of 1.5 Celsius in reach. We can't do this in the United States without offshore wind. It will accelerate our ability to tackle all of the issues related to climate. And involved, as you could see from the previous presentation, there's government, business, and civil society really engaged in this process. And then we have to think about the transformation, and some of the other speakers will talk about the technology, but there's information, there's data, sound policy, and market instruments all will play a role in making offshore wind a possibility. Next slide, please. So as we heard from Tashara, there are call areas that have been designated and those that are in the process of being designated as well. So as of May, this is the map in detail of offshore, eastern US, and then we have the Gulf and the West Coast and Hawaii. Next slide, please. So the importance and the significance of offshore wind, I alluded to in my first slide. One, that it is critical for the US to meet its climate goal of 50% reduction in greenhouse gases in 2030 and net zero by 2050. And we see that offshore wind development, and I think we have to think of this as a development process, is gaining momentum in terms of project scale and scope. And I know that our speaker from GE is going to really talk about the scale and scope of the opportunity. As I said, offshore wind contributes to state energy goals, economic development, and equity opportunities. So I think that with offshore wind, we really have the opportunity to think about meaning of equity in its most important and meaningful way. And most important for us as we sit here today is that the decisions we make today related to offshore wind at the state and federal level will impact the future. Thus, what we do today is very important for a successful process and development tomorrow. And that really has to be the perspective at this point in time as we consider the growth and the opportunity of the industry. Next slide, please. So underlying offshore wind, we see a national market opportunity. First of all, we know that it's an abundant resource, as we could see from the BOEM slides and from my previous slide. The other thing is that we're in the process of leasing, and as I said, we're into the other COP, the construction and operation that is going to be ongoing once this COP is over. What we need to understand is that the states in particular and the country, as part of decarbonization, is going to increase electrification. And this becomes very important when we think about offshore wind, particularly the grid. And another thing that we have to consider is that offshore wind has zero commodity cost, But as we know, it isn't always reliable. It's intermittent. So this also is important related to the development of other technologies, and particularly batteries and hydrogen. And then we also have to think about the impact of offshore wind as fossil fuel retires. I'm sitting in New England and we're seeing retirements of fossil fuel plants, and we can expect more. And how are we going to fill the gap? And obviously offshore wind is a critical way to do so. Next slide, please. So when we think about the development, we have to think about the wind farms themselves. They are massive generators. And associated with this massive generation are supply chains. Our financial financiers are supporting the development. And as I said, the technology. So really, the onshore and offshore grid, as we know, is huge infrastructure. And how we integrate offshore wind into the existing onshore grid is really a very important technology issue, a very important social and policy issue. Let's look at, for example, the interconnection points, the POIs. Where are they going to happen? And then, as we have more POIs going into the onshore grid, should we be considering an offshore grid? How are we going to configure it? Who is going to control it? Who is going to govern it? All of these become aspects as we begin to think about the policy issues of offshore wind. And this is part of the conversation about what we do today influencing tomorrow. We're not saying stop development of offshore wind, but we really need to consider who makes the decisions related to the offshore grid and how they're implemented. The other issue is the issue of data. We really need good data, siting, permitting, protection of wildlife and fisheries. So all of these environmental aspects need to be given equal weight. And what we have learned is that projects can be stopped when a stakeholder, for example, the fishing industry, finds that they're not being satisfied by hearing their voices being heard, and that they too are getting consideration. Finally, issues relating to pricing. The pricing of offshore wind, we're seeing the costs fall, but what do the pricing of the projects really mean? Who is going to pay for them? It's a complicated issue to most people, and we need to get better transparency in these issues as well. Next slide, please. So we have a strong commitment to offshore wind on the federal level, and the procurement really happens at the state level. And I'm going to go into this in a little bit more detail. There are RFPs issues, there are purchase power agreements signed, there's a development of ORECs or offshore wind RECs. And when these agreements are signed, we have pricing assumptions that last for 30 years. Of course, there's risk, there's development risk, there's price and regulatory risks, and all of these risks are borne by different stakeholders. There's the equity and economic impact of the new industry, the opportunity and the growth for jobs. All of this is tremendous, but who really benefits, and how are these benefits spread out for those people living across along the shore, and also those people where the infrastructure is being built, and how do we benefit? And what we have recently seen in New England is a power line coming from Canada was just rejected by the state of Maine. So infrastructure and how it's handled and brought to the population is going to be a very important issue for us as well on the offshore wind side. So all of this becomes important. Next slide, please. So my question is, here we are seeking 30 gigawatts of offshore wind. Is this really achievable within the decade? It's questionable. I'm not sure that it is, but at least it's an aspirational goal. And when we look at the benefits, we're looking at jobs, an enormous set of jobs. They just can't be one-off jobs of project development. They have to be ongoing. We're talking about clean power, which is really important. We're talking about the removal of carbon from the atmosphere, all of which, and we're talking about huge amount of capital investment. We're talking about manufacturing plants to build the blades. We're talking about supply chains, but we're also talking about the building of new vessels to put the wind pylons in place in the ocean floor. And we have something called the Jones Act in this country, which means that we're going to have to build our own vessels in the United States. And we're also going to have to upgrade our ports. This means jobs, but this also means disruption, all of which we have to take into account from policy perspectives. Next slide, please. So as I said, many states have clean power plans and have really committed themselves to clean energy, and offshore wind is an important part of that. And I'm going to go into a little bit more detail to give you some insight on how 2 major states are handling offshore wind, but just to understand that it's a phenomenon around the entire country. Next slide, please. And some states, and particularly states that really are planning for offshore wind, have also established roadmaps to clean energy. And it reinforces the point that offshore wind plays an important part. And if you're interested in learning about sort of where the states are going in more detail, these roadmaps are really very helpful in understanding transition to clean energy. Next slide, please. So here is, and I hope you can read this slide, is where the major offshore wind states are at this particular point in time. It's really important to understand what authorizes clean wind. For some states, it's legislation. In Massachusetts, we've had a whole series of laws where we keep upping our target to clean wind. We set timelines. We figure out the contract path forward, which becomes very important. And within each tranche, how much wind is being requested and what our target year is and what our capacity is. So this is just a helpful slide to see that 30,000 number, but also sort of where we are and the challenges ahead. Next slide, please. So how do we procure offshore wind? This is building off of BOEM. Usually it's the developers and the generators who bear the initial development costs. And what their costs are will become evident in their responses to the state RFPs, requests for procurement. Usually the method of procurement is a purchase power agreement. And the state of New York, New Jersey, and a few other states have created a very particular REC, or renewable energy credit, called an OREC, the Offshore Wind Renewable Energy Credit. At the end of the day, in an OREC regime and in the Massachusetts regime, we still sign long-term contracts, or PPAs, and we need these PPAs from the financial perspective. Obviously, we're seeing the cost of offshore wind drop. It's still expensive. And I think that we're going to have to accept and understand that we're going to need federal subsidies for a while. Offshore wind has a capacity of about 45%. There are times that the wind won't blow, and then we're going to need batteries, storage, other opportunities to continue to deal with these intermittency problems. Next slide, please. New York and Massachusetts have slightly different procurements. I think this slide is pretty hard to read, but the essential point is that in Massachusetts, we had legislation. In Massachusetts, it is the EDCs, the electric distribution companies, which up until now, with the state playing a lesser role, have been responsible for the procurements. In New York State, it has been NYSERDA, the New York State Energy Research Development Authority, who is doing it. So you can take 2 different models, you end up in the same direction. And the reason New York has 2 approaches is because in Long Island, it happens under the control of LIPA, the Long Island Power Authority. Next slide, please. So in Massachusetts, what happens, and this is a Massachusetts procurement, you see the offshore wind generators, they send in the energy, the EDCs, the distribution companies, receive the energy, and they send the RECs, and they send some of that to the ratepayer, and some of the wind goes into the wholesale market, and the RECs are separated and go to the supplier. What we found in Massachusetts is that it might be better to give less control to the EDCs, some of which themselves have now become partners in offshore wind development, and I think the state may play a more important role. But more important to Massachusetts is this notion of a price cap. When Massachusetts first procured offshore wind, they said that each project had to be successively cheaper. Well, that looks great for the ratepayer, but if you are looking to get other benefits, non-ratepayer benefits from offshore wind, developers may be less responsive in a state where they see price caps than other states. And I think Massachusetts recently experienced such a situation and may be considering changing its price cap regime. Next slide, please. This is the New York State OREC approach, where the generator sells energy into the wholesale market, and the ORECs go to NYSERDA, and then NYSERDA sells the ORECs. The bottom line is, in both models, it's the ratepayer who will ultimately foot the bill, at the same time seeing benefits as well. Next slide, please. And again, just building on to Shara's points, this is where we are at this moment. Right now, Vineyard Wind, which this slide shows 0 megawatts, has achieved financial close. We're expecting those 800 megawatts to start coming into the New England grid through Cape Cod eventually. But again, we see where we are at this moment in time by state, and which of the states, really from Maine to North Carolina, are very engaged in the offshore wind process. Next slide, please. And again, this is sort of another reconfiguration, looking at the states, looking at the timelines, looking at what's procured. It's just very helpful to see what a large commitment these coastal states have made to date. Next slide, please. Another big issue is offshore wind transmission and grid integration. We don't have a lot of time to discuss that. Maybe it's an issue that will come up in the question and answer. It's very important. Right now, the generators play a lot of role in the interconnection, but really FERC is looking at this in a NOPR that it is just issued as part of a broader infrastructure look at grid integration. How we configure the offshore grid will become very important. We don't want to stop the process, but we just have to say that this is going to be a very costly infrastructure build to get offshore wind into the grid. Next slide, please. And finally, we've seen from my presentation that there are a lot of challenges. A lot of things are uncertain, but we really do need to achieve the promise of offshore wind. As I said, there are development challenges. We have to look at more closely what kind of foundations we'll be using. We'll have to look at supply chain, ports, installation vessels. These could delay offshore wind if they're not done in a timely way. So even these aspirational goals could be delayed or to a point in time where we won't meet our targets. The environmental challenges are very real. We see the clean air and the emissions reduction, but their impacts on birds, right whales, the fishing industry, all of which have to be considered. I mentioned the infrastructure challenge, the grid integration, the siting, the role of FERC, the independent system operators, and the states are all going to have to get involved. Pricing challenges. Yes, prices are falling. We still are going to need federal subsidies, but we need to, as consumers, better understand the true costs and benefits of these projects. And finally, public engagement. And this relates to equity. What is meaningful engagement? At what stage of the process does it happen? Otherwise, we're not going to realize the jobs, the goal of the price reduction, and ultimately the clean energy. So we have a lot of work to do, and I look forward to hearing from our other speakers as well. Thank you very much.
Thank you so much, Dr. Kate Garnick. Next up on the hit list is Dr. Danielle Merfeld from GE Renewables. Over to you, Danielle.
Thanks, Jim. I'll just start by saying I'm so pleased to be here to be a part of this colloquium series, in part because I think offshore wind presents some of the most exciting engineering challenges for the engineering community. So I'll really be focusing, on what are some of those challenges and opportunities as we think about growth here in the US with this market. Next slide, please. So we've heard from both Tashara and Barbara a lot about these first few points, so I won't repeat them, but I would say just the idea that the United States has this really fantastic wind resource, especially in the Northeast part of the country, is something that we, at this point in time, taking advantage of that for our growth is probably one of the best things that we can do in energy that we haven't done already, and getting started at this sort of new level of effort is going to be an exciting undertaking for everyone. And I think one thing you maybe heard, but I just want to reinforce it, about half the country lives within 50 miles of the coast. So when you think about our population centers and how to bring renewable energy to where the big load centers are, this is probably one of the most direct ways to do that. You've heard a lot about the state government support just recently, and of course at the federal level and BOEM leadership. I'll mention just on this last bullet that as a OEM, a manufacturer of this kind of equipment, I think this is a great opportunity for the United States to benefit from all of the work that's been going on in Europe mostly, but around the world in this space. So a lot of very experienced players, whether they're building these pieces of equipment, financing them, moving big equipment around and doing installation, that's something that we'll be able to bring to our first generation of projects, which should give us a good get started pace in this industry. Next slide, please. So getting into a little bit more details on the technology, let me just tell you some of the language that we use just to put us on the same framework. So when we talk about cost, and cost is probably one of the biggest drivers that we point our efforts in engineering towards in the offshore wind space, we refer to it as, we use levelized cost of electricity as the metric. It's really a way to measure the average net present cost of electricity generation over the lifetime of that generating asset. So it's a good way to compare apples to oranges when you are comparing various resources and power plants of different types. So the levelized cost of electricity for offshore wind is the goal. There are several things that you can do in the design, in the manufacture of a wind turbine to impact that cost. And what I show here on the left are the top cost drivers and what that means for the design of the wind turbine. I won't go into a lot of detail, but I just want to give you some of the high level points of view. The number one cost driver for wind turbine value and the cost of offshore wind is going to be the capacity factor. And capacity factor, it just means it's the ratio of the actual energy that's made over a period of time to the maximum possible energy. So this is in part due to how often is the wind blowing, how much is the wind blowing, but also how efficient is this turbine at catching that wind and at effectively and efficiently translating that mechanical motion into electricity. So the way to think about this is if we reduce the capacity factor by 10%, that's the blue part of the line, we'll increase costs by 11%. So we don't want to do that. If we increase the capacity factor by 10%, we can reduce costs by 9%. So you see how this table works. The second cost driver, the second most important thing for us to impact is the capital costs. How much does this system cost? And this one is if we reduce the costs by 10%, we actually, if we reduce the capital costs by 10%, we can reduce the cost of the electricity by 8%. And this is because the turbine isn't the only thing we're spending money on to develop a whole offshore wind farm, but it's a pretty important part. So I won't go through the whole details because certainly how much your cost of capital and what it costs to operate a wind farm, those are also very important. But the big takeaway here is that the number one impact here for cost reductions has to do with the turbine size and scale. So longer rotors, higher power rating will give you lower cost of electricity. And that's what's been driving the industry globally. If you go to the next page, this is just a kind of a snapshot of what scale we're talking about. And this is I mean, it's not hyperbole to say these are the largest moving machines humanity has ever built. These are incredibly large assets, and they're moving farther and farther away from the coast, so they won't be seen. But a 14 megawatt, or even in this case, now a 15 megawatt offshore wind farm or wind turbine is on the scale of the Eiffel Tower or the Chrysler Building. I mean, these are huge systems. So, and just one little fun fact here, one rotation of these size turbine blades, just one rotation could power a home for 2 days. So having these hundreds of these out in the ocean creating power, I mean, it's easy to think about it in numbers, but it's hard to relate to them sometimes. So it's just a magnificent amount of energy that we can access with something that's a free resource. So if you look at this page, maybe the things to take away are, what are going to be some of the technology development that we need to continue to reduce cost, especially when you're looking at this huge scale? And one category would be around the controls, which controls is just another word for the brains of the system. So if you can make your system smarter, where it can maybe help self-commission when you're installing it, or it can learn as it sits in a site and adapt and be more resilient to the environment that it's in, or more efficient, that improves your cost because you can essentially have your system be more efficient or a better operation over the lifetime. Another technology arena that we like to think about with next generation and how do we continue to reduce costs is additive manufacturing. So just like in any industry, when you use additive manufacturing where it makes sense, you can reduce your part count, you can optimize weight, and weight's a really important thing for these offshore systems, and I'll talk more about that in a minute. One specific weight is the powertrain, you know, the system that changes the motion of the wind into electricity. It's a pretty important part of the system, and the more power dense it is, the smaller and lighter it can be. It can fit into a smaller area, and any 1 pound of equipment you put at the top of this tower adds about 1.5 pounds almost of weight in the tower. Imagine having to hold up a heavier object. You need to stabilize that even more. So material and cost are pretty well balanced. If you put $1 at the top of the tower, you need to put $1 into the $1.40 or so into the turbine. So any amount of efficiencies of weight, you get paid back more because ultimately then you don't have to hold that extra weight up. So efficiency on weight is a big one. And the last area of technology I'll mention that can radically change the cost over time is just around the wind farm integration. So that electrical balance of plant, how are the wind turbines connected to the system that goes to shore, even how the turbines interact with each other as an integrated part of a wind asset. You know, right now, each wind turbine can operate in a way that maximizes its efficiency. It catches as much wind as possible, transfers as much of that into electrical energy as possible. But what if the wind farm is situated in a way that when the wind comes from a certain angle, the turbines behind those front turbines are now in the wake, they're receiving less of that wind energy. So as a whole system, the first turbines might be getting a lot of energy, but the ones behind it aren't. What if the wind turbines were adaptive enough to optimize themselves, behave more like a flock of turbines rather than a bunch of individual turbines, and those front turbines could yaw out of the wind just a little bit, enough to move their wake so that the ones right behind it could have a boost more wind. It's slightly less efficient for those first turbines, but could be dramatically more efficient for the ones behind them. So that's just a very high level example of how you can change the output of a system by making it smarter. And there's so much digital technology and integration, especially now that we have artificial intelligence and machine learning. These are all technologies that apply to offshore wind. Next slide, please. So thinking about beyond the turbine itself, because that's once in an operation, there's great ways to imagine making it more efficient, making it better, but making it, the process of manufacturing it, there's a tremendous amount of technology opportunity here too. And I would say it's driven primarily by the fact that the scaling, the size that we're working at now requires us to think differently. So we have to think in a completely different way to be able to efficiently manufacture these blades, is the example here. This is the inside of a blade factory. And the picture at the bottom here is actually one of our offshore wind blades just after it was built, before it's got the paint coating. And I don't know if you can see, but these are people in the picture standing next to it. This blade is 107 meters long. So it's essentially the length of the football field plus the end zones. this is an incredible large system, and being able to make this, we just can't make it in the same way we made it when it was 20 meters or 40 or 50 meters. It requires a completely different mindset, and that's part of what the industry is doing to innovate manufacturing. Other things besides the blade are, how are we thinking about new equipment to last longer in a saline environment, or how do we harden some of the ball bearings and parts of the gear systems that are used, or the pitch systems that move the blades around to catch the wind best. All of this in bringing automation to it, but also new materials, new design techniques. All of the manufacturers in this space are looking at how to improve the process. And we're going to really lean on our suppliers to invent and invest as well. If you go to the next page, I'll say besides manufacturing these things, even just putting up our first prototype of our latest model was a learning experience in and of itself. This is just some pictures of when we were building our first prototype back in 2019 in the harbor at Rotterdam in Holland. And this was one of the first times we've ever had to manage some of the weights. So the picture at the top here is the nacelle and the hub on the top, second one in on the top. That is heavier than anything that we've built before, because of course this is larger. Our first offshore wind farms were 6 megawatts. This is now 15 megawatts. So the size of that nacelle is big, but it's also heavier. So this is the first time we used 2 cranes to lift something that big. And you can see the whole process of building this turbine, even though this is onshore, it's in a harbor, so it's close to the water to get the good wind. But the tools and techniques we're going to use to put this offshore, now that we've built these, we have a big farm off the coast of France with many of these. This is a different, this is a different way to think about offshore. Our offshore sites today are based on, from my personal perspective from GE, we have a lot more of the smaller turbines, and these larger ones are going to be going up very soon. So the rest of the world is kind of building out offshore, and I think we're going to do a lot of learning that we can bring to the United States. Next page is really thinking about risk. So one of the reasons why there are so few developers and operating and equipment leaders in this space is because it's hard to do, and there's a tremendous amount of risk in doing it. So one of the key things around introducing technology into the space is how do we reduce risk at all stages of the technology development, all the way through to the deployment of the system. So the components themselves, we have to think about the design specifications, getting certifications on everything from the materials to any individual component. And we can test those in labs, and sometimes we even have our suppliers test them before sending them to us in terms of an assembly or manufacturing flow. The other piece is we have to test things once they're integrated together, mechanical and electrical integration. We'll do this in factories typically, either within a tower factory, for example, or a turbine factory where we're assembling parts of the nacelle. At the system level, we can't just test the subsystems apart. We have to combine some of them and do a full nacelle test before it's out in the ocean. We have to be able to test our blades for 20 to 40 years of operation before, within a year, so that we can understand if that design holds up. So the system tests are also critical. And then, as I just showed you on the last page, building prototypes, putting out that whole system all at once and understanding how it changes in different environments, different performance factors, that's going to add another cycle of learning. But we can't jump right to that. This whole flow is really critical to ensuring that we don't overextend on the risk side. The next page will really show you a good example of how we're thinking about lowering costs a little bit out of the box. So this beautiful ship is, it's called the Jules Verne. It is what's called a service operation vehicle. This is where people get on this and go out to the wind farm. It might stay out there for several days. This is essentially a high-tech vessel that's our floating mission control center for services. Our wind farms, usually an offshore wind turbine needs to be visited about 5, sometimes double that times a year. And sending a person out once at a time or once in a while, it just doesn't work. This is a more effective way to go out and service the fleet or the farm. And those visits can have a lot of minor or very major activities, including things like changing a blade or just having a couple people go up and lubricate some of the systems. And some of them can use this kind of a vessel. We have a lot of capabilities on a vessel like this, but I wanted to show some of the infrastructure, including what we just used for servicing. that's required to service this kind of an industry, because it's quite different from obviously what we need for onshore wind, which this country has certainly a lot of experience with. Other things that are going to help us lower the cost of service and lower the amount of times we need to go and visit these offshore turbines are certainly around design validation. We got to make sure what we put out there works the way we expect to and performs the way that it's expected, even under very extreme conditions. You know, hurricanes are not going away. We have to live through those, and severe storms out in the coast. Also, digital solutions. As I mentioned before, there's been tremendous progress here. So having remote ability to do things from shore, or being able to have smart O&M strategies, even robotics is going to be critical. And let me move to the next page real quick, because I think this is the next couple points here I just want to make quickly. The supply chain is a big part of our solution. If you could go to the next page, please. Having the right solutions and at the right ports with the right capabilities, it's that we're going to need volume in the market to drive confidence for investment in our supply chains. This is at ports, this is with suppliers, servicers. It's a very complex ecosystem. The next page is a little bit more detail on that, essentially showing some of the vessels that we would need. There's very few vessels that can carry the kind of offshore wind components that we're talking about. And the few that are there, we're going to need multiples of them to grow at the pace to meet this 30 gigawatts by the end of the decade. And by the end of the decade, some of those vessels will be obsolete because we'll even move to bigger, larger systems. And we have some market restrictions that we have to work around here in the US, such as the Jones Act, meaning that we need to have US flagged and fleet vehicles. So we can't really borrow the fleets that exist around the world to come here and grow ours. We have to grow our fleets as well. And similar, our harbors have to be developed so we have more space. Next page, I just want to get to quickly. You heard about floating offshore. This is just today a very niche segment. There's a lot of technology that will come into play here. And it's important for the US because 60% of our resources are in deep waters that we can't have standard foundations. So we're going to need one of these, just a few examples shown here on the right. Costs will come down and we're going to want to access a lot of those new resources, but it can only be done with this new approach. And I would say the biggest hurdle today, besides the actual foundation, the floating foundation development, is the controls. Having a system that's so has to be under so many different conditions, operate efficiently over such a long time, requires really strong control of that system. And then the last couple pages, if you could just go to the next one, please. I just want to say it's not enough to make the power offshore. You have to get it to onshore. And there's a lot of pieces to this technology challenge and operational challenge, from getting it to an offshore electrical platform and then converting that to be transformed and sent undersea to the land. This is just an example. Many of our offshore wind farms today, and the only one we have in the US right now is an AC connection. But if you go to the next page, what you'll start to hear more about is the increasing amount of wind farms that are connected to shore by an HVDC connection. And really the trade-off here is cost, and maybe the best way to think about it is there's a break-even point for when you move from AC to DC, because AC is relatively cheap on land, but it starts to attenuate greatly and it's more lossy underwater. So the break-even point, whether you're choosing AC or DC, is about 800 kilometers for overhead lines and about 50 kilometers for buried or undersea cables. So if your offshore wind farm is more than 50 kilometers offshore, you're probably going to choose HVDC. And if not, you could go with AC as a cheaper option. But just to give you a perspective, that big yellow box there, that's actually as tall as a 15-story building. That's the electrical converter that holds the HVDC system. As wide as a football field. It's built onshore and towed out to sea and then connected to the wind farm. So these are, again, big engineering challenges and feats of impressive capability that we're building. And I just think it's important to understand that's not enough to have the wind farm. Connecting these to shore and getting them integrated into our electrical grid is probably the bigger challenge today that is standing between us and our 2030 goal in the US of 30 gigawatts. So I'll just wrap up on my last page by showcasing those points that I've been making throughout here, starting with technology, the supply chain development. Reducing risk is not enough. We also need the infrastructure development and continuously learn from what we're doing. And with that, I'll pass it back to you, Jim.
Thank you so much, Danielle, for that great presentation and a great introduction into our next speaker, who will be talking about the grid interconnectivity and the electrical adventures offshore. Dr. Raja, over to you, sir.
Good morning. Thank you for inviting me for this panel. And I'm happy to be talking from the energy capital of the world, Houston. So I'm going to talk about more on the applications of the offshore wind, because you heard about the policies and also what are the problems with some of the wind turbines and the blades and that type of things. What are the challenges? Now I'll focus on the applications. So next slide, please. So I will talk about the offshore wind for oil and gas extraction plants, including the subsea systems, how offshore wind can be used, and offshore wind for producing green hydrogen, and offshore wind for shore power and powering the vessels, and offshore wind for integrating with the onshore grid. Next slide, please. So the deep water oil and gas production, they need a lot of power. Hundreds of megawatts of electrical power is needed. So presently they are all produced or mostly produced from the gas turbines located on the platform. They will be driving the generators, or sometimes even the gas turbines will be driving directly the compressors and pumps. So use of these gas turbines with fossil fuels, they generate 80% of the total carbon dioxide and NOx emissions from offshore installations. So there is a good opportunity for using the offshore wind to power these offshore oil and gas production systems. For example, here you can see that there is a wind farm, offshore wind. So there are a number of platforms. So these platforms can be directly powered from the power generated from the offshore wind. Of course, you need to have an inverter, another platform where the power conversion has to be done, and then it will be power has to be supplied to the different platforms. So this is one example. Next slide, please. So this is, for example, it can have its own microgrid where the offshore wind is supplying to one platform. This shows, for example, wind, this is the 5 megawatt generators. They're all connected together, and it is easy to parallel them, the power on the DC side. So you need to have a generator output is going to the AC-DC converters, and then there is a DC system. And then from DC, then you have the inverters, which can drive the various pumps and compressors and various other loads. And also the offshore wind can have can be used to connect it to the onshore grid. For example, this is a DC to AC inverter. And this is similar to what we have seen in the previous slide, or the slide by Danielle from GE, that yellow platform that was showing the power conversion system. So this is the one that you can have here, and then it can be transferred as an AC power system to the utilities on the onshore. So this synergy between the offshore wind and offshore oil is already underway in Europe, where a number of companies are already engaged in using the offshore wind for oil and gas production. So another, next slide, please. I try to move myself. So another opportunity for offshore wind is the subsea oil and extraction field. The trend in the oil and gas industry is to go for everything for the subsea production system. Means we talked about producing the power generation on the platform. So instead of power generating the platform and every individual load, like the pumps, compressors, and several other electrical loads, they will have a separate bus going from the platform to the individual loads. So instead of having like that, you can have the entire distribution on the seabed. So that is coming up, and several companies are working, or many major oil companies and Siemens, ABB, they're all exploring that. And they've also tried installing several of the electrical systems under the ocean. So that requires a power sea grid has to be designed at a depth of about 10,000 feet. And then you don't need any platform. And it can go as low as 30,000 feet of depth. Of course, there are several challenges in putting the electronics, like power electronics, under that depth, because the pressure is another criteria. For every 10,000 feet, the pressure increases by 100 bars. At 30,000 feet, there is 300 bar pressure. So the systems have to be designed to meet that pressure, and also the corrosion. And also, how do you service the equipment if something fails? So how do you bring it to the ocean, onto the top of the ocean, and service them? So there are issues, but there are several companies find it is much more advantageous to use the subsea power grid and bring the power to the subsea plants directly. So a lot of work has been done bringing the shore power to the subsea power systems, using HVDC lines or HVAC lines, or even low frequency AC like 16 and 2/3 hertz. That type of work has been done, but still there is a lot of work has to be done in this area. Next slide, please. So now you can use for the subsea, instead of getting the power from the shore, you can use the offshore wind. And so this is the subsea system. This shows. So if you are using the power from the grid, this cable can be hundreds of kilometers. So we can, instead of using hundreds of kilometers subsea cable or power cable, we can, if you use the offshore wind, then we save a lot of power, and also offshore wind can be efficiently utilized. And it can power a lot of the subsea pump motors, subsea compressors, and there are several other loads I will show you in the next slide. So again, the distribution power is, distribution voltage is around 36 kV, and the power can be 10 to 15 megawatt, the compressors, and the total power can be as high as 100 megawatts. So next slide, please. So this gives an idea for one subsea plant, how much power is required. This is just a typical example. For example, pumps can take up to 10 to 15 megawatts, and there are other electrical systems that need lower power. So if you add all these things, it needs hundreds of megawatts of power. So that can come from the offshore wind. Next slide, please. So just to give the problem with the wind energy is it is stochastic in nature. The load is fairly constant in the subsea power systems, except when you suddenly a motor starts or shut down the system, then it can. So this is an average power can go like this, and maximum. This is the maximum, and this is the average power. So if in this type of systems, if you use the offshore wind, how do you take care of those type of transients if we have the wind energy supplied everything? So we have a small consortium in our university where we are working on subsea electrical systems, where Chevron, ExxonMobil, Shell, Technip FMC, Siemens are all members of our consortium. And also we have a Subsea Systems Institute in the University of Houston. So how do you take care of this stochastic nature of the wind? So we are trying to combine the offshore wind with fuel cells and battery energy storage systems so that you will have a stable grid. So even in case of any transients or if there is no wind, we can still supply the power to the subsea loads. And excess wind can be used to generate the green hydrogen. For example, we can have an electrolyzer there and supply the fuel cells. And I have shown here as an example of a solid oxide fuel cell. because you have a natural gas already extracted. You can have a reformer. Only when there is no green hydrogen is not available, you can have either a blue hydrogen or a gray hydrogen that is coming from the reformer and the natural gas. And another advantage of using solid oxide fuel cell is we can combine with the gas turbine and have the efficiencies greater than 65%. We can operate as a combined cycle system. So that is one possibility. So we are investigating various strategies and combining with the BESS system to compensate for the offshore wind or any other, or combining with even looking at even floating solar photovoltaic cells. Next slide, please. Next slide, yeah. So another application of offshore wind that is being examined by several companies, for example, the DNV is looking at using the offshore wind, particularly floating wind turbines, for injecting the water into the oil wells so that you can enhance the recovery of the oil. So the main purpose of the offshore wind here is to run those compressors and also the water treatment equipment that is required. All those things are run by the offshore wind energy system. So for example, 8 companies, including ExxonMobil, ENI Energy, Nexen, they're all joining together, developing a 6 megawatt wind turbine system that is used for this injecting the water into the oil wells to enhance the recovery of the oil. And also another application is to use the wind energy to have a desalination system. So that can also run from the offshore wind energy. The next one, please. The second application I'm talking about is the green hydrogen production. So this is I've taken from this US Department of Energy 2021 report. So several companies and industries are looking at producing the green hydrogen. Green hydrogen is producing the hydrogen using the electrolysis system. For example, Shell, RW, and several other companies are planning to use 10 gigawatt of offshore wind energy to produce hydrogen and pipe it to Europe. Okay. And the goal of these efforts is to produce up to 1 million tons of hydrogen from 2035. And there are companies like Ørsted and POSCO, that is a South Korean company. They plan to use 1.6 gigawatt of offshore wind capacity off the coast of Incheon, that is in South Korea, to power its hydrogen production requirements. And also Neptune Energy's Poseidon. This project will integrate offshore wind, offshore gas, and offshore hydrogen for Dutch utilities. And then the Ørsted H2RES, the 2 megawatt wind to hydrogen project, will use companies' 3.6 megawatt offshore wind turbines to produce 1,000 kilograms of hydrogen per day and power zero emission road transport in the greater Copenhagen area. So there are several work going on in producing green hydrogen from offshore wind energy system. Next slide, please. So another company, Tractable, has been involved to produce an estimated 15 tons of green hydrogen per day via a 400 megawatt analyzer from, or 400 megawatt electrolyzer from offshore wind energy at an industrial scale using electrolysis. So the company see enormous potential for carbon dioxide neutralization using by producing green hydrogen using offshore wind. Next slide, please. So another application of offshore wind is for shore power for powering the vessels. Companies like Wärtsilä, they are all looking at use of offshore wind for shore power for decarbonization. For example, if the shore power is coming from the offshore wind, that is a renewable energy, and the vessels are all powered, then we can eliminate a lot of carbon dioxide emissions that is generated by connecting all those vessels to the power grid when they are at the shore. And also, if the vessels are not traveling very far from the shore, they can be used, depending on the size of the vessel, they can be used for charging the batteries if they are purely electric, or if it is a fuel cell or hydrogen base, then the hydrogen that is generated can be used to fuel those vehicles. So there are a number of proposals to develop offshore wind in California coast, including floating wind farms. For example, in 2017, California mandated that at least half of all container ships run on shore side electricity at berth. So means that power comes from the offshore wind. The next slide, please. So another major application that is already happening is the offshore wind power integration to the onshore grid. So in the previous speaker talked about the HVDC system. So we have offshore wind, then you have HVDC to DC HVDC system where AC is generated. If it is a HVAC system, or you can have a HVDC system where the generator output is converted to DC and transmitted over long distance. And recent trend is to use the voltage source inverters. So you can have hundreds of kilometers of HVDC transmission. The advantage of HVDC system is no need for reactive power compensation, and also the power loss is lower. So there are, of course, several challenges because it is HVDC. How do you protect the system? Because there is no natural zero crossing of the current, and also very small network inductance compared to AC systems. So the fault current can be very high. And so there are a lot of work going on in this area, including in our lab. We are also looking at various protection strategies using hybrid circuit breakers and that type of DC circuit breakers for the HVDC systems. Next slide, please. So offshore. So what are the challenges to integrate wind power to offshore grid? Intermittency of wind power. I think we already discussed all those things. Very clear. Lack of short circuit capacity. So the short circuit capacity in a power system is an indicator of its robustness. So since wind power are interfaced with frequency converters, their contribution is limited to SCC. The short circuit capability of the power converters. And also because of the interface with a lot of power converters, so there can be a negative damping and also harmonics. And with the integration of the offshore wind with the battery systems and other energy systems such as fuel cell and others, so that also can create the overall reliability of the system. It can affect the reliability of the overall system. So that needs to be addressed. And next one is my last slide. So next slide, please. Yeah. So in summary, the offshore wind has a lot of applications for extraction of oil and gas, or for using the offshore wind for extraction of oil and gas. And that way, we are reducing the use of gas turbines on the platforms to generate electricity. That will further reduce the carbon dioxide emissions. So offshore wind can be used for generating hydrogen and transported to shore for various applications. And offshore wind can be used for powering the vessels and for grid integration and for desalination plants. And of course, there are a lot of other challenges. Operation maintenance costs also are very important, and due to intermittency of the wind power, high penetration in the offshore grid is not possible for stable grid operation. And we need large backup batteries depending on the system. Thank you.
Thank you, Ron. What I'd like to now have happen is, could all the panelists please turn their cameras back on and join us on the screen? And I'll ask you to keep yourself muted unless you're speaking, so that we don't have a lot of crosstalk feedback. All right, we had a lot of very nice questions that were submitted, but and some of them have been answered by the panelists online, some of those that were very specific. But what I've done is I've taken the questions that have come in and I've tried to affinity group them into broader discussion areas. And so let me start, and this is a question I'd like to hear from multiple of you on, but there were a lot of questions that involved environmental impact, and it really covered the spectrum, all the way from doing environmental impact assessments to trying to understand what would happen to birds and to fisheries, et cetera, both for the turbines as well as for the power converters. Do the power converters, for example, when you cool them, do they cause localized heating that might impact marine life? So just a whole broad area of environmental impact, from bureaucracy, if you will, to the actual impact on fish and birds. So who would like to make some comments about the environmental impact of this? Don't all talk at once.
Yeah, I'll start, just because I think that's been, you know, the idea of the design of the turbine and its impact locally has been something that we've addressed quite a bit, and well, I mean, good questions. So I'm glad that the audience has been so focused on this. It's something that we have to consider. If we're doing this to help the environment, the last thing we want is to create a negative environmental impact with these systems. So I'll mention a few of the points, Al, that you just made. With respect to the localized heating, all the power electronics systems won't be underwater, except for if there's, I mean, we're talking about platforms, and many of the electrical systems are in the nacelle, so at the top of the tower. Even in some onshore, at best, they're in the base of the tower, but not under the water level. So none of the heating would be an impact on water. And if it were, it's such a small point of heating in a massive sink, I don't know that we would be able to measure much of that. Secondly, I think there's a question about sea life. Our turbines were the first ones here in the US on Block Island. It's, you know, there are 5 6-megawatt turbines sitting off the coast of Rhode Island. And there was a tremendous amount of studies, assessments before, during, and after the development of that wind farm. And what we found, happily enough, as we went through, there's certainly good estimations of how this would impact sea life positively. But from what I was expecting and what I saw as the outcome, it was even better than I had hoped, in that there was it was acting as an artificial reef. So there was a tremendous amount of increase in sea life activity. So the fishermen were happier than they thought they were going to be. Certainly the tourism is great, because people want to go out on the boat to see the turbines up close. But, you know, whether it's oysters or lobster or fish, I think it's been a net positive for the environmental, you know, the seabed life. So that's one good point. And I think Northern Europe has also seen improvements in terms of sea life where they have offshore wind farms. And then lastly, I answered one of the questions that came in, but I think whenever people think about wind farms, they also think about migratory animals, birds or bats, certainly much more of an impact on land. But what we've learned from having wind farms be developed on land around the world is tips and tricks for how to mitigate and minimize that. Some of it is in the siting, so you don't put a wind farm in the middle of a migratory lane for birds, or you turn them off during certain migratory periods where you need a week or even days or hours of the night or day when you expect them to go through. But generally, there are also ways to deter bats or birds from flying through a dangerous zone of wind farms, which are being developed, new technologies all the time. And I just mentioned, just in the last few months, there was a great study just painting one blade black for offshore wind farms can reduce the amount of bird strikes by like over 70%. So an impressive number. I think we're going to continue to see innovation that helps reduce any negative impact. But I also want to highlight that there's some pretty positive impact here too that we should, you know, take advantage of and celebrate.
So I would love to build on some of Danielle's points here. I think that it's very important to look at it in several ways. First of all, decisions that we're making today are going to impact tomorrow. So what decisions we make about foundations, what decisions we make about the technology today will totally impact tomorrow. And so we have projects in place, but what are we going to do looking forward? So I think that's an important sort of point to make. The other point is that this is where data becomes important. And I think that we need to make investments in data done by the federal government. And I know that DOE is starting to do that so that we can really, make the best assessments. But you're right, we have a trade-off between greenhouse gases in the atmosphere, how we even configure, all of the costs and benefits. So I think it's a really important point going forward. The other point I need to make is having to do with the process. How do environmentalists, how do coastal communities get a seat at the table? I think there was a great quote in the chat, if you're not at the table, you become the meal. So we need to figure that out, in a way that has meaning for those impacted, but at the same time, delay costs money. And we have to be cognizant of that as well, because people will pay for the delay in terms of financing and other costs. So it's a very complicated question, and I don't think we have all the answers, but I think we have to be open to many considerations.
Any special considerations for doing environmental impact assessments in a marine versus a terrestrial environment?
I'm going to turn that over to Bohm. I think there are many. That connection between the offshore and the onshore is absolutely critical, just in terms of bird migration in itself. That I'm not an expert, but I'm thinking that perhaps Shara may have some data and information on that as well.
Shara?
Yes, we've been working very closely with Fish and Wildlife Service to better understand the migratory pathways, especially in the Gulf of Mexico, because that's my area of focus. As Danielle mentioned, painting one of the blades black, understanding what those seasonal migrations are to power down the turbines during those seasonal migrations. So these are some of the things that we're working with, not only with industry, but also with Fish and Wildlife to better understand what do we need to do in these areas. And so one of the reasons why we moved the call area too, because we noticed those migratory pathways were largely off of Louisiana near Breton Sound, off of Mississippi. So we moved those call areas, but further defining those areas, working with Fish and Wildlife to understand where those breeding colonies are. So when we bring those cables back, we're not going to disturb any nests. We'll probably potentially run those cables through the existing right-of-ways that we already have, or run them along with the lines with the pipelines that we already have. So we're not going to continue to disturb any habitat, but just utilize what we've already had. So those are some of the things that we've been working and talking with Fish and Wildlife about.
Raj, you want to make any comments?
No, I think they have answered.
Okay, very good.
I think Danielle answered whatever I wanted to say about power electronics. So
okay, very, very good. There's also been a number of questions that compare and contrast terrestrial versus marine use of turbines. Everything from the cost to install it, the cost to maintain it, given how difficult a marine environment can be with moisture and with salt, the cost of decommissioning. Compare that to the length of time, the percentage of time that it's actually online because the wind may be more reliable in marine environments. So general comments around that whole broad spectrum of comparing terrestrial to marine generation of power. Whoever wants to go first.
Go ahead, Barbara, and I'll go after you.
No, you go first and then I'll follow, because you probably have some of the technical aspects of it that I don't.
Yeah, well, I just think probably the best way to think about the differences in terrestrial versus marine power are your cost structures are just different. What drives a better system cost offshore is bigger, fewer turbines, because then you have fewer foundations, fewer cables, fewer turbine visits, all those things that are quite expensive. On land, especially in the US, where we don't have we don't have as many constraints as, say, Europe, we can actually use more land, smaller turbines, more efficient collection of electricity. You really just want to site it close to a transmission line or to an interconnect site. So the drivers for what makes a good wind farm design are very, very different for onshore and offshore. That being said, there's lots of things that are similar in terms of material use, low weight, a lot of the factors are the same, but the big drivers for cost efficiency and reliability can be very different. That's generally my answer.
I would just like to add that we are really starting with almost like a tabula rasa offshore, whereas onshore, the issue of siting, for example, in New England, except in northern Maine, it becomes very, very difficult to site an online wind plant. I have many scars from attempting to do so. And I think that, the siting issues become very, very important and very costly when you're talking on land. The siting issues are different, obviously, offshore. So that's one thought. But I think the important thing is to recognize this grid integration point. And for example, New Jersey, which has the New Jersey Public Utility Commission as well as PJM are looking on the offshore-onshore connections. So I think that, as we understand that better from a pricing perspective and from an infrastructure perspective, I think we'll be in a better place to connect the offshore and the onshore and just look at it part of the development of the grid, which is ultimately going to be onshore.
Just transferring the power from offshore to the onshore is not a major problem because there is a lot of work has already been done. More last 30, 40 years, there are a lot of HVDC lines. Like even in the United States, Pacific Intertie and many other things, they were all connected under the ocean. Even under the ocean, there are a lot of power lines going. So transferring the power itself is not a major problem. Then whether should we put the wind turbines on the offshore or onshore? Of course, onshore there is already there is a limited space, and people always complain that we don't want to have it in our backyard or farms, and so many things are affected. So offshore, in a way, is better, less of disturbance. Once it is installed, and the reliability, once installed, I think offshore should be fine. And reliability, some people question. I think generally, even we are looking for even power electronics to put under the ocean 25 years of reliability of things. So how we can maintain the system, because it is not easy to repair the system once it is in the ocean. So there are a lot of work. I think Danielle can talk more about that one because she really does she produces it. I just study it. So they do a lot of work on the reliability issues. I think it should not be a major problem.
Danielle?
Yeah, and Raja just mentioned something that probably needs to be addressed as well. Besides, absolutely, he's right. The reliability for offshore is a more costly challenge. We can't have reliability issues cost a lot more to fix if you're offshore, for sure. One thing though that we haven't mentioned, I guess it's probably worth driving home this point, is that when you have onshore wind farms, though they can be quite large, generally on average, they're not as many megawatts as offshore wind farms. And they're also much more dispersed and tied into our national grid infrastructure in a variety of places. So the density of these new variable speed or variable renewable energy technologies integrated to the grid through power electronics, not through synchronous generation, is relatively dispersed. When you have massive amounts of renewable energy coming in to a relatively weak grid, I would say, meaning that if you start to influence a lot more of the percent of the penetration of power on that grid is coming from renewable energy, now you're going to have the challenges around the stability of the grid. Again, technology exists to manage that issue, either putting synchronous condensers on, using grid forming technology. These are all things to help stabilize the grid operation. That will be more of a challenge when you have a large amount of offshore coming into a coastal region that doesn't have a lot of conventional generation right there nearby, which I would say the Northeast US does not. So that's probably the biggest challenge, not building the HVDC line and bringing it in, but the integration point on land to our grid.
Well, I need to add from a policy perspective. We can talk technology, we can talk all sorts of things, but we also have to say, what are the policy implications and who benefits by the interconnections and the implications for siting and everything along that line. So I think that we have to look at these problems holistically in a way that we might not have traditionally done so. That integration may happen technically, it may be technically possible, but let's think of all of the other implications that often are borne by the ratepayers of the electric distribution companies. So there are cost implications and a lot of things going forward as well. So let's look at it a little more holistically than we might have in the past, I think would be helpful.
So very much related to this issue of grid stability and so forth, we had a number of questions asking about energy storage, comparing and contrasting batteries versus generation of hydrogen that you would then use subsequently in a fuel cell, for example. So comments on how you integrate energy storage. Do you do it at the turbine? Do you do it at the converter? Do you do it on land and so forth?
Yeah, can I just go? Yeah. If we are looking at integrating the battery energy storage with the offshore wind energy for offshore applications, then we don't have to do it on the shore. We have to do it in the ocean. So probably on a platform, or now the companies are looking at putting under the sea everything, that is the subsea systems. But integration itself should not be a problem. How do we do it? Generally, the integration is mostly done on the DC side because AC side paralleling sources are difficult. So we convert so for example, AC generators are normally AC only. Nobody uses DC generators now. So the wind turbines drive the AC generators. They will be converted to DC, and then there will be DC-DC converters depending on the voltage that is required. Even for the battery, depending on the size of the voltage of the battery, there will be DC-DC converters. So they can all be integrated together, and it is converted to required AC, whatever it is, either 50 hertz or 60 hertz, mostly 60 hertz system. So integration itself is not a major challenge because whatever can be done onshore can be done on offshore. Only in offshore it has to be done on a platform because we are still not ready, or the technology is still not advanced to put everything under the ocean. But the research organizations like SINTEF in Norway and even ABB and Siemens, they're all working to put whole power electronics, batteries, motors, everything under the ocean for oil and gas extraction systems and for maybe for other applications.
Okay.
I'll just add real quick that many times when we integrate storage into our renewable energy systems, that hybridization is for the purpose of expanding the effective capacity factor. So for example, in solar, you can expand by 4 hours the effective sunshine value of your system. So it helps manage peaks when the sun is setting, but people are coming home and turning on lights in their homes. In California, that has actually been a real measurable value of adding storage to solar. With wind, it obviously has the same benefit that you can sort of move peaks around. You can extend the capacity factor, the effective value on the grid. Offshore wind has a much higher capacity factor already. Our offshore systems and most big ones, ours are over 60% capacity factor. That means unlike our previous systems or even the beginning of wind, which was in the low 20s, our onshore wind farms are over 50% now. So the higher the capacity factor, the less necessary storage is, but whether it's hours or days or weeks or even seasonal, different types of storage are integrated at different points. For wind farms, solar farms, it can be in the converter, it can be at the substation, it can be in the HVDC converter system, it can be at a fax line, just at the AC transmission level. So there's a whole scheme of capabilities to integrate storage, and that doesn't include, this is batteries that I'm referring to. We also have pumped hydro storage, long duration storage through other non-chemical methods that I think at the grid level, we just have to think of this as a very complex system of systems. There's no one way to do it. It's actually valuable to have the diversity of where we integrate storage.
Great. So this one, I think, Trishar, is one that you should start with, but we had some questions involving the special challenges and opportunities you would find in the Gulf relative to either the East or the West Coast. So what are some of the real opportunities that you have, and what are some of the special challenges that the Gulf brings? Obviously, hurricanes are one of them, but there's other things as well.
I think the opportunities is the existing workforce that we have, the existing facilities that we have, and to actually make the platforms that's going to be needed, the 6 bottom platforms that are going to be needed. We have the expertise and utilizing that expertise to get the nation up and going. The other thing is that workforce. They're used to going out offshore, servicing, platform servicing, using those servicing vessels. So I think those are the tremendous opportunities that we have in the Gulf of Mexico. And as I mentioned before, also is the challenges of the hurricanes. Now in the Gulf, there are lower costs for energy already in the Gulf of Mexico. But after speaking to industry, the companies that submitted on the RFI, that doesn't really seem to frighten them. However, they are thinking about utilizing green hydrogen in their process as well. So capitalizing on green hydrogen and wind technology in the Gulf.
Great. So Danielle, is there any difference between a turbine that you would put off the coast of Texas and one that you put off the coast of Maine or the coast of Alaska?
I would say just like with onshore wind, we tailor our configuration of our turbines to the wind speed, because we're trying to optimize both for efficiency and capacity factor, being the largest driver of cost. So if you put too large of a wind blades on a turbine and you don't have as much wind speed, it really won't turn as often. I mean, that's just the physics of it. So in a lower wind speed environment like the Gulf, the turbine blades might not be as long as they would be, for example, in a high wind speed area off the coast of New England.
Great. See, we've also had a number of questions around the supply chain for offshore wind and looking at both the domestic supply chain, the international supply chain. Should we try to bring more of it onshore? I think all of us now are observing issues with the supply chain as we come out of the pandemic. But has recent events, anything driven your thinking about whether we need to onshore the supply chain or make it more international? But just your thoughts on supply chains and how it impacts where we're going to go in trying to achieve this goal by 2030 and then 2050.
Well, I'll just mention, besides the general need to grow fast and we'll have as much of the supply chain close to the output as possible, the whole idea of our supply chain breakdown recently has put it in new light. So I also am concerned and I focus a lot on our sustainability. What is our footprint for our system? Not just the turbine lifetime footprint, but building the turbine, servicing the turbine. And in our business, one of our biggest parts of our carbon footprint as an operating business is logistics of moving large things around the world. So the more we have big, heavy castings built in Asia and shipped to Europe or to the US, that part of our footprint is not sustainable. So I think one of the reasons why we want to drive localization, besides having the ability to grow quickly with jobs created near the opportunity and where near the projects are, which certainly drives government support and local support, is just reducing the footprint. And luckily technology allows us to do that much more easily these days with more automation, more additive technology, higher value jobs, less sort of dangerous, dirty, boring work. So I think it's really a culmination of technology, policy, and opportunity that is driving much more local supply chain development.
So I think this is a very important policy issue on several fronts. Number one, what we're seeing is that the states who are developing or supporting offshore wind are in somewhat of a competition. They want the jobs, they want the port development. So it's an interesting interaction, and how the states over a period of time learn to work together and cooperate on these issues, I think will benefit the population as a whole. The other question is, what are these jobs? Are they long-term? What is the training associated? And how do these jobs become stepping stones for a whole group of people in the future? And I think that all of this is part of the supply chain. One of the interesting issues are the installation vessels. And what we have in the United States is, due to the Jones Act, we're highly limited on the installation vessel side. This is a real problem. And even though we're building them, this is a real issue. This is an opportunity for delay. So I think that supply chain is a critical issue, but that gets to the benefit of wind and the pricing and the long-term contracts. have we signed contracts where there are real benefits, particularly if the ratepayers over a period of time are going to be paying the costs of those projects? So it's a very big question relating to supply, and it's something that we need to keep in mind as well.
Good. We've had other questions that involve, the social impact of all this. That, if we're trying to get to 30 by 30, as we've been talking about, you've got to get the power onshore. So maybe we build them far enough off the coast that you don't have to see them. But when the power comes onshore and you need to put the infrastructure there, how are we engaging the coastal communities that are going to be part of this? This is maybe very much a policy question, Barbara. But how do you actually make sure that the communities are going to have to deal with the infrastructure, feel like they're part of the conversation and part of the decision making, and not just being used?
That is such a critical and important question on so many different levels. First of all, the issue of the regulatory processes are very complex. They're opaque. They're not transparent. Oftentimes, you only know that something is happening by a notice in the paper. I'm not sure people are reading the paper today. So there has to be a grassroots, deeper focus on communication from the start of the planning function. I'm not sure that people even know what BOEM is, yet there's a major role for communication, grassroots communication, so that people know these projects are going to happen over a period of years. Right now, I'm watching the projects develop in Massachusetts. I think the companies are making very good faith efforts to communicate. I'm not sure that it is happening in the way that we should be communicating. I'm coming to the point where I think probably we need to pay for intervention in some of these processes and give grassroots organization the skill sets, the knowledge to understand the processes. Well, if you're going to pay for intervention, somebody is going to pay for intervention. Who should be paying for the intervention? Is it all of us? I mean, again, one solution leads to another policy issue. And I think that if we don't do this, it's a question of diversity, it's a question of inclusion, it's a question on multiple levels that we need to see I think, a revision. And the only other comment is many of the companies that are coming are European companies. And I'm not, even though they have US partners and they think they're really addressing diversity, I'm not sure that they are at a really basic level. So that needs to happen as well. It's a big problem and we have to address it on multiple levels.
Good. So another human factors kind of question, I think maybe Raj and Shara, this one falls mostly in your lanes. But, we've been operating in the Gulf for a long time with, oil drilling, et cetera. We've had some incidents there like Deepwater Horizon, the Macondo well. Are there things that we've learned from our experiences in the oil industry, accidents, et cetera, that are readily transmittable into making sense and helping us with offshore wind? Raj?
Yeah, I think there was a study by, who did that? David Daniel was leading that study, NAE Council. So they did a lot of work on what are the safety aspects that needs to be considered. They put a report. I don't remember the report. It was about 6 years ago. It was done, or more than that. But right now, of course, that has been taken care of. What if, as a part of our consortium, that is why we are, I always, whenever I give a presentation, I say my presentation is the electrification of oil and gas. So as we electrify more and more of these systems, instead of just simply depending on one, that BOP, that is called that one that is used for, what is the expansion of it? I forgot. So that is, instead of that one, we are developing a lot of protection circuits based on the electrical circuits, like DC circuit breakers and others, so that prevents many of these power transmission faults and that type of things. But for the oil itself, that I think oil companies are now doing a lot of work on that type of things. That's why we haven't seen any major that type of things the last 6 or 7 or 8 years. I think maybe Shara can talk more about it.
Tushar, from your perspective?
Yes, there's always lessons learned that we can take into account. We have been working very closely with DESI, our sister agency that handles the enforcement. Right now, we're working out an agreement because currently the way the regs are written, DOM is responsible for the safety portion for offshore wind. However, we're working very closely with DESI so that they will be the partner with us for the offshore wind for the safety. So working with industry to get those standards, understanding what those standards are, and to make sure that industry understands what the standards are as we move forward.
Okay, good. See, another area of questions, this both has a policy and a technology piece to it. Are there any specific things that if we could accomplish them in policy space, it would accelerate and improve our chances of actually making the 30 by 30 goal and the 2050 goal? And are there any sort of magic silver bullet technological advances that we need in order to achieve those goals behind where we stand today? So that's probably a Danielle and Barbara to start with.
Well, I think that there are so many issues, and I don't think there are magic bullets. I think that there are a lot of lessons learned over a period of time that we really need to integrate into our discussions. And I think that one of the things that we have an opportunity, or one of the areas, is that we can't be siloed anymore in our approach to this. There's a technical piece of this that has a lot of implications, but we also have to make sure that voices are heard and that there's a process. And we also have to understand development, and we have to acknowledge development risk. And that becomes a part of it as well. So again, it's a multifaceted question. I don't have a silver bullet, but I think that what we have to be very sensitive to are all of the players in the field, and yet be able to have a way that we can move forward on a clean energy approach. And that's why the various states have their own perspective, but there's a major role for the federal government and obviously the developers, the financiers, and everybody along the way. So I know it sounds like a broad answer to a question, but I think there are a lot of lessons learned, and we have to learn them quickly.
And I'll just add, I think that was a great answer Barbara just gave. Having as much information on the table as possible and as much open dialogue about what's needed allows all the players to come with their best ideas. You know, we can bring technology solutions to equity challenges. We can talk about developing the supply chain and needing a consistent growth market to invest. I mean, if we're all upfront and aware of the overall challenge, then I think policy government players find the right ways to bridge the gaps. And there are some, I think, fundamental gaps today that we need the federal government to step in. We need to enable a different way to think about transmission planning, or we need to understand the cost of not doing something so that we can compare it to the cost of doing something. And that's not anything one state, one company, one supplier can do.
So another question, which is in some ways sort of paradoxical, but no, the whole idea behind going to renewable energy, of course, is to reduce CO2 emissions and use that in an attempt to control climate change. But on the other hand, there's a certain momentum behind climate change that's already there. And so do you see climate change, rising sea levels, for example, having any impact on where we go with offshore wind? I mean, if it's a fixed foundation, you have to worry about blades hitting the water at some point and so forth. But what about the feedback of climate change on our ability to generate offshore wind?
I've asked that question a lot, and I'll say and I've also seen some good questions come in along the same vein there. Every time I have looked into it for our own designs, the measurable impact of those things are outside of the realm of a lifetime of our design, 40 years-ish. So obviously there are going to be extreme weather events that are sooner. I mean, right around the corner, they happen all the time, they're happening now. it's not going to be a full-scale change that you would expect a turbine to live through continuously in the near term. So I think we focus on resilience through events rather than new paradigms of operation. I guess, so my main focus from a climate change perspective is how do we design systems that can be more resilient to these extreme events? And in the future, they might need to operate differently, but that's not part of the challenge today.
Okay, good. So another question that in fact, you touched on this a bit, Tushar, when you were speaking. But if you take a look at the number of trying to produce 30 gigawatts by the year 2030 and where we stand with the leasing right now, are we going to make it and get enough leasable area into the mix to make the goal by 30 by 30?
Yes, that is our hope. Based off the existing leasing areas that we have and the upcoming leasing areas, we are hoping to reach that goal.
One other interesting question that came up is that, and I guess we could say that this has actually happened with hydropower, that you build dams and it has an effect that you maybe didn't intend ahead of time. Is there any risk that we're going to get to the point where we take so much energy out of the wind patterns that it ends up impacting the weather in and of itself? Have people done that kind of modeling, or is it just such a small piece that it's just going to get completely overwhelmed by the entire weather ecosystem?
So the short answer to that is it's too small to notice, and it will be overwhelmed by the much, much bigger weather ecosystem. However, and I called this out in one of the answers, there was a really cool study done several years ago after Hurricane Sandy hit the Northeast. And it was a very academic view based on models about how many turbines would you have needed in the Northeast to have reduced the wind enough to mitigate some of the storm surge in New York City. And it was something like 780,000 turbines, like on the order of 300 gigawatts, so 10 times more than what the state has planned. And they would have had to be tightly oriented in a portion of the path of the hurricane. So nothing in the near term for any of our plans, but by doing that, the model showed that it could have reduced some of the wind forces enough to reduce the storm surge. So even with this, 100-year ahead, tightly packed kind of offshore wind resource that's not in our future today, it still only just reduced some of that wind. In a generic environmental wind setting, I would imagine it maintains a negligible impact for quite a while, just because the spacing and the design of a wind farm is so that you don't overlap your wind too much.
I agree with what Danielle said, because it is not going to affect the environment in any way. For example, if we have a terawatts of solar energy, then how it is going to affect our solar radiation falling on the earth? Somebody asked. It is not going to affect. It is there already, and same thing. The wind is not going to change because you are taking it and using it as electricity. So that should not affect. And there are other questions maybe previously about what is the work that is being done on the 2010 oil spill, anything, some question. So I mentioned BOP, the blowout preventer. So after that, there is a lot of work has been done to how to make it more and more effective and more workable, and a lot of research has been done on that. There are several universities and even the energy companies are looking at it so that there won't be any repetition of that failure of that BOP or blowout preventer. And there was also another question, maybe we didn't answer, you asked earlier about the hydrogen, production of hydrogen, and battery use of hydrogen is better, or how long we want to use the battery, and that type of question you asked earlier. I think the battery is only used for a short time. We don't want to use the batteries for a long time. For example, overnight, if you don't have a wind power, for example, or the wind power is very low, the batteries will not be able to provide the power for that long. Then it will be a very huge battery pack. On the other hand, the hydrogen, if there is a fuel cell system, then you can use that hydrogen to generate electricity and supply the power all night. So there is a difference between using the hydrogen and the battery. Battery immediately comes into effect. If there is a sudden drop in the electricity or electric power, due to sudden increase of load, then battery can come and operate and provide the required power. Whereas battery is more for even in electric and hybrid vehicles, we use battery for power in the hybrid vehicles, for example. In electric vehicles, it is the energy is important. So battery is for providing the energy rather than the power. So like that, so battery is going to provide the required power for a short time.
Great. So I see that we've come to our end time here. So let me thank all of the speakers for their presentations and for the discussion. And I would like now to turn it back over to Jim. Jim.
Thank you, Al, and thank you to Dr. Raja, Dr. Garnick, and Dr. Merfeld, and Ms. Matthews. Thank you so much for the gift of your time and your insight and perspectives. We're very excited to have had this opportunity with you. We're very lucky that it coincides with the discussions going on in Glasgow, Scotland right now. And we look forward as the Gulf Research Program and the National Academy of Engineering to leverage our discussions from today as we move forward in our joint programs. As I mentioned earlier, we will have a recording of today's presentations available, and this is the web address where they will be at. But you can you'll be able to Google this this colloquium and find it as well. We anticipate having that up within about 10 days. We have to go through some obvious time to process and things of that nature. But with all that being said, thank you again for all of you who have joined us today. We look forward to the continued discussions, and we look forward to the continued work with all stakeholders involved in this important national imperative. Thank you for your time, and have a beautiful weekend.